Hello and welcome. Today we're going to be looking at the unit test for integration and accumulation of change. This has lots of questions. We're going to go over every single one to make sure you understand how to approach and solve these kinds of problems and are ready to master integration, a vital part of the study of calculus. If you like these videos or find them informative, please be sure to like and subscribe. And with that, let's get started on our first question. Let's go. Alright, so we are given the definite integral from 0 to 1 of 4x over the square root of 1 minus x to the 4th. Alright, how do we approach this problem? Let's think. Well, if we look at the denominator, right, the 1 minus x to the 4th, we can think that looks kind of similar to some of our trigonometric derivatives, or inverse trigonometric derivatives, right? So if you take the derivative of the inverse of sine of x, you end up with 1 over 1 minus x squared, right? If you take the derivative of cosine of x, the inverse of cosine of x, you get negative 1 over the square root of 1 minus x squared, just the negative of the derivative of inverse sine of x. Then take the inverse of tangent of x, you get 1 over 1 minus x squared. I think that's what it is. But this one seems to align with, it's positive first off, so it seems to align with sine. And so we're going to try it out with the sine. Alright, so what we're going to do is we're going to try to get into a form where we can write 1 over the square root of 1 minus x squared. Right, because that is what the antiderivative, or that is what the derivative of inverse of sine of x is. So we're trying to get that, and then we take the antiderivative. So how are we going to do that? And how are we going to do that? Let's think. Well, if we take this problem and we set x squared equals to u, right, we're going to use u substitution. Right, now, if you're unfamiliar, u substitution is kind of like doing the chain rule backwards. Right, that's essentially what it means. So what you do, I'm writing stuff down in a notebook if you can't tell. So, so you have x squared equals u. That's how I'm defining it. Now the critical part here is that I'm going to take the derivative of both sides, and I get 2x dx equals du. Okay, so what does that mean? Well, it means, right, this is the part where you apply the chain rule. That's how you do the opposite of the chain rule, 2x dx equals du. And then if I find somewhere to put 2x dx, I can substitute in du. So I'm going to take out all the x's and put a bunch of u's in there. So how am I going to do that? Well, doing that, right, the numerator is 4x, and then you have times dx. So I can make this definite integral of 2 times du, right, which replaces the 2x dx, the du, over the square root of 1 minus, well, it's supposed to be x to the 4th, but when we're using u substitution, we don't want any x's at all. Right? We don't want x. So we can change x fourth. Well, x squared is u, so x to the 4th is u squared. And we end up with this. That is what we end up with right here. Right, so this is the concept of u substitution. So it's not that difficult. There's a couple of basic steps. So first you set u equal to something, right? Something that you want to, something that you can substitute in like the definite integral that you started with. You take the derivative of this, something dx equals something du. You try to find somewhere to put the something dx in to put in the du. Right? So it's very important that you search for like some definition of u, where you can take that derivative and plug it in somewhere. And then you just replace all the x's with that substitution for u. And now you end up with 2 times du over the square root of 1 minus u squared. Now the other thing is the limits of the definite integral, right? Are they going to be 0 or 1? Well, no, they're not going to. Well, they wouldn't just be 0 or 1 because x is equal to 0 or 1. Because now we're doing this in terms of u. So you have to figure out what u is. So you have to plug in that 0 into x squared equals u, and you get the u is still 0. You plug in the 1, and you get that u is also 1. So in this case, the 0 and 1 will just stay there. But usually, if you plug it into, you get different limits of integration than what you started with. All right, now the 1 over square root of 1 minus u squared, that's sine of x, so that you're going to write that as 2, or inverse sine of x. So 2 times inverse sine of x, 2 times inverse sine of, well, the inverse sine of u actually, sorry, because we're going in terms of u, so it's inverse sine of u, right, that's what that antiderivative is, and you're going from 0 to 1, okay, 0 to 1, like that. Right, remember that this is just one of our rules that we memorized, right? You inverse sine of x gives this 1 over square root of 1 minus x squared, or u squared in this scenario. And then of course, remember definite integrals or integrals in general are just going to be an application of the antiderivative, right? You find out take the derivative of something to get what you have. So you're going backwards. Make sure you remember that. And it's going from 0 to 1. So you just plug in both 0 and 1, and you get 2 inverse sine of 1 minus 2 inverse sine of 0. Well, inverse sine of 1 is going to be pi over 2, so it's going to be 2 times pi over 2. They're always operating in radians in calculus. And calculus is based on radians, right? Like all of the trigonometric functions in calculus only work if you have radians. All the time. That's the only one. And then minus, well, it's inverse sine of 0 is just 0, so it's going to be minus 2 times 0, which is just going to be pi. So the answer to this is going to be, and we can move on to the next question. All right. Function g is graphed, and we're asked to find the integral from -4 to -1 of g of x dx. All right, so this is a good time to think about what exactly the integral is defined as, not in terms of like how you take the antiderivative or the fundamental theorem of calculus, but I just want to know, like, if I'm just given not a function but just this, what does that mean? What it means, what the integral means, is that I'm trying to find the definite integral at least. I'm trying to find the area between two different points, right, in between the x-axis and a curve. Okay, so I can have -4 is right here, right, and -1 is right here. All right, so essentially, I'm just trying to find all this area, right? We usually define it as area under the curve. This one is so it's going negative, which means that it's going to have a negative. It's going to be a negative area under the curve because it's technically not under the curve; it's over the curve. But in any scenario, the amount of area in here is going to be, well, we can make a triangle here. Right here we just apply some basic geometric knowledge to try to find the area here. So this is a 2 by 2 triangle, so it's going to be 4 divided by 2 is 2. So 2 here. And then you have 4 squares here. Another 4 squares here. Right, so is that what it's going to look like? Yes, it is. So that's going to be 10. Our answer is 10. And we can keep going. Alright, so that is incorrect. Let's think about why it is incorrect. Alright, it's incorrect because we didn't put the negative sign in there. That's why you always remember the negative sign. Alright, that's why you always remember which direction it's going. This is the area over the curve, so you need to make sure you remember that -10 is there. Let's keep going. Approximate the area between the x-axis and g of x equals 2 to the x from x equals -2 to x equals 2 using a trapezoidal sum with 4 equal subdivisions. Right, so what does a trapezoidal sum mean? What does that mean? Well, a trapezoidal sum means that you take each of the subdivisions, right? So from -2 to 1, that's the first one. From -1 to 0, from 0 to 1, and then from 1 to 2, and then you find the you make a trapezoid out of that, right? So you have the base, right? So you have one is here, and then you go up here, and here, and do this, which connect trapezoid. So essentially, you're doing the length of this, which is 1, times the height of the height of g of 1 plus g of 2 divided by 2. So if we were going to write this down, right, then we have, we're using g of negative 2 plus g of negative 1 over 2, right, since the area between each subdivision is just 1, so it doesn't really matter, we don't have to multiply by that, plus g of negative 1, or g of negative 1 plus g of 0 over 2 plus g of 0 over plus g of 0 plus g of 1 over 2 plus g of 1 plus g of 2 over 2. Okay. Now the g of negative 1, g of 0, and g of 1 all have 2 each of those cancel. Or they don't cancel, but you have g of negative 2 over 2 plus g of 2 over 2. And then you just get to add g of negative 1 plus g of 0 plus g of 1. Those are going to be equal. G of negative 2, that's going to be 2 to the negative 2, that's 1/4. Over 2 is going to be 1/8. And then you have g of 2, which is going to be 4 over 2, which is going to be 2. G of negative 1 is a half, plus g of 0, which is 1, plus g of 1, which is 2. And that's going to give you 5 and 5/8, which is also 45 over 8. 45 over 8. Okay, 45 over 8. That is our answer. And we can keep going. Okay. So now we're trying to find the integral, the indefinite integral of x to the negative 3. So this is where we use the inverse power rule, right? So let's think about it in terms of like a power, right? So if we took the derivative of x to the negative 3, we'd end up with something x to the negative 4. Okay, so to get 2x to the negative 3, if we started with x to the negative 2, then that would, if we took the derivative, that would give us negative 2x to the negative 3. So if we just put a negative 1/2 in front of that, then we get x to the negative 3. And then, of course, you have to add the c, always. Right, because if you take the derivative of the c, it cancels out, so it really could be anything. So you have negative 1/2 x to the negative 2. Right, you do power rule, you bring the negative 2 down, this cancels out, and you have x to the negative 3. And we can keep going. Alright, now we're trying to find the integral of 2x minus 5 to the 10th. Alright, so let's think, right? So if we had 2x minus 5 to the 10th, then we're taking the derivative of that, that would give us something 2x minus 5 to the 9th. So we need to start at 11. 2x minus 5 to the 11. Now if we take the integral of that, the derivative of that, we get 11 times 2x minus 5 to the 10th. That's going to be over 11. But we also have to use the chain rule, so we're also going to have to take the derivative of 2x minus 5, which is times 2. It's going to be another 2. So that's going to be times 2 in the denominator to cancel that out, and we end up with 2x minus 5 to the 11th over 22. Over 22. So our answer is D, and we can move on. Okay. Now we have f of x, piecewise function, x plus 1 for x less than 0, cosine pi x for x greater than or equal to 0, and we're trying to evaluate the definite integral. Well, since this is 2 parts, we can just split it into those 2 parts. Alright, so we can split it into negative 1 to 0 of x plus 1 dx plus 0 to 1 of cosine pi of x dx, and that's going to be equal to what? Well, the antiderivative of x plus 1 is going to be 1/2 x squared plus x, right? If you're wondering how I knew that so quickly, it's just because lots of practice using the inverse power rule, right? You start to understand how the things work. And then for cosine pi of x, well, that's going to be sine, it's going to have to be sine of pi of x to start with. right? That's going to be what you start with, sine of pi of x. That's what you started with. Now, if you're starting with sine of pi of x, and you take the derivative of that, you're going to end up with cosine of pi of x times the pi. Alright, so you're going to have to cancel out that pi by doing 1 over pi. It's a 1 over pi times sine pi of x. And that's the second one, so then you do that. You put that in the brackets with 0 to 1. And then you just plug stuff in. Or you plug in -1, you end up with 1/2 minus 1. When you plug in 0, you end up with 0. So it's going to be 0 minus 1/2 minus 1, which is going to end up being like a half. And then you have plus second one. So if you plug in 0, you're just going to get 0. If you plug in 1, you're also going to get 0, because sine of pi is just 0. So that's plus 0. So it's just going to equal a half. 1/2. That's it. So it's just 1/2. And that is our answer. Let's keep going. Okay, the graph of function f is given along with the area of each region. The graph forms the x-axis. Find the definite integral from -4 to 5. Well, -4 is here. -5 is here, so that's all this area. So you're starting at 0, right? Because that's how sum works. You subtract 6 and you add 4. Subtract 6, add 4, and that gives you -2. Let's move on. Okay, so here we have a definite integral, and we're taking the derivative of it. How does that work? How that works is we just take the, so the variable has to be at the top. If it's not at the top, then you have to make a negative and flip it. But the variable is at the top, so you take when you take the derivative of that, you instead of t, you put x cubed. So you have sine of x cubed. But then you have to multiply by the derivative of x cubed, kind of like the chain rule, which is going to be 3x squared. So our answer is 3x squared times sine x cubed. Alright, and that is our derivative. Let's move on. Alright, so now we're moving on to the next one. Evaluate the integral of x times e to the negative x. Alright, so let's think about how we do this one. So this one, you actually cannot solve with our usual integration techniques, which are, we use the inverse power rule, right? We use, we just use the general inverse that we already have, and we have u substitution, right? That's kind of like the tools in our toolbox right now. And right now, we're going to expand that toolbox by adding something that we call integration by parts. Integration by parts. It's a very important concept, and it will help you a lot of times, right? Integration by parts, you use when you're multiplying two things, right? So you have x times e to the negative x. So that's why we're going to use integration by parts. So when we talked about u substitution earlier in this video, right? We said it was the inverse of the chain rule, right? We're kind of like doing the chain rule backwards. That's what the u substitution is. Integration by parts is like doing the opposite of the product rule. Okay, so let me show you. So say I have f of x, g of x, right? And I'm taking the derivative of f of x, g of x. Right, so the derivative of f of x, g of x. Okay, and that's going to give me f prime of x times g of x plus f of x, g prime of x. Okay, that's what the product rule says, right? So it looks like this. Looks like that. Okay? Now what I'm gonna do is that I'm going to take the integral of both sides. Okay, so now the integral of the derivative of f of x g of x is going to equal f of x g of x. So I'm just left with f of x g of x. And that's supposed to equal the integral of f prime of x g of x dx plus f of x g prime of x dx, because I can split that up because they're added, right? Into like something like this. right? That's what it looks like. Now I can subtract, say, the second one off, right, from both sides. And I end up with f prime of x, g of x dx is going to equal f of x, g of x, minus f of x, or g prime of x, with the integral of f of x, g prime of x dx. Like this, the bottom one. Okay, that is what we're doing right here. Okay? Now the way we usually write this is by using f of x as u, g of x as v, f prime of x du, f prime of g is dv. So we're going to write this as integral of v because g of x times du is going to equal u v minus integral of u dv. Okay, so that's what it's going to look like. So we need to split this x times e to the negative x into a v and a du. Okay, so we need to choose these carefully, right, to make sure that it's easy to do stuff later with them. Okay, so I'm going to choose, let's see, I'm going to choose I'm going to choose v to be, choosing v to be x. Alright, so v is x. V is equal to x, which means that du is going to equal e to the negative x. Right, so I'm writing it like this. So I'm writing it down. Right, and if you're wondering why it's diagonal, well, I'm going to show you, it's kind of like a table. Right, so I'm going to have this. This is the table. Okay, this is what the table looks like. Okay, so now v is x, so dv is just 1. And then du is e to the negative x, so u is the integral of that, or negative e to the negative x. And I know that the integral and the derivative of e to the negative x are both the same thing, which is just a coincidence, and it's a property of the exponential function. But that is how it works. So now we just take uv. So v is x, u is negative e to the negative x. That's going to be negative x e to the negative x minus the integral of u, negative e to the negative x, times dv, which is 1. Alright, so it's going to look something like this. This is what we got right now. Okay, now the integral of negative e to the negative x is going to be e to the negative x. So then we end up with negative x e to the negative x minus that integral, which is going to be e to the negative x. And make sure you look at the signs. And then, of course, you have to add the plus c. And then this is your answer right here. That's your answer. Negative e to the negative x, negative x times negative x times e to the negative x minus e to the negative x plus c. If you don't believe me, do the product rule, right? Figure this one out. That's what it's going to look like. Now I have to make it look like something there. So we're going to factor out a negative e to the negative x. And we're going to make this x plus 1. X plus 1 times negative e to the negative x plus c. That's going to be this one right there. And we can keep going. Okay. Evaluate the integral from 0 to pi of x sine 2x dx. Okay, so this is going to be the same thing, right? The integration by parts idea. Okay, so how are we going to set this up? Well, we can pick v as x, right? Remember, for v, or whichever one you're taking, whichever one you have for second, you want it to have, you want it to be something that if you take the derivative of it, it doesn't really become that complicated, right? It becomes less complicated. That's why we're making it x, because the derivative of x is 1, and that's super not complicated. And then du is going to be sine 2x. Right, sine 2x. So u is going to be the inverse of that, which is going to be negative cosine 2x, but you also have to have a half. So negative 1/2 cosine of 2x. And then dv is obviously just 1. dv is just 1. So then I'm going to plug that in to my uv. So uv is going to be negative 1/2 x cosine of 2x minus integral of u dv. So that's going to be minus the integral of negative 1/2 cosine of 2x, because v is 1. So the negatives are going to cancel out. So you're just going to have plus integral of 1/2 cosine of 2x, which is going to be, well, it's going to be sine of 2x here. And then since you have another 2, it's going to have to be 1/4. So it's going to be negative 1/2 x cosine 2x plus 1/4 sine 2x. And when you're dealing with these kind of functions with something in the middle, it's very common when you do integration by parts to have the first one be like something to the first power, like 1/2. Second one is going to be 1/2 squared, 1/4. That's really common. But we have our function right here. All right, we've made it negative 1/2 x cosine 2x plus 1/4 sine 2x. All right, now we just evaluate it from 0 to pi. At both the 0 and pi, the sine of x is going to cancel out, right? It's just gone. And because sine of 0, sine of 2 pi, they're both 0. Then I'm going to plug in pi for negative, if I plug in pi and 0 for the first term, the negative 1/2 x cosine 2x, well, the 0 is just going to cancel, right? Because that's that. And then the pi is going to be negative 1/2 pi, negative 1/2 pi times cosine of 2 pi, which is 1. So it's going to be negative 1/2 pi, negative pi over 2. Negative pi over 2. That's our answer. And we can move on to the next question. All right. Okay, so now we're trying to find the integral from 0 to 5 of negative 2 g of x d of x. Okay, so how do you think we're going to do that? Well, if we just try to find the integral from 0 to 5 of g of x, that's just this. So that's going to be 4. And then you have this minus 2 that you're multiplying by. So that gives a negative 8. And we can keep going. Graph function f is shown below. Let g of x equals the integral from 0 to x of f of t d of t. Evaluate g of 3. So g of 3 is going to be integral from 0 to 3 of f of t. So from 0 to 3, it's going to be all this. That's going to be that space. Right, so I can immediately draw this rectangle here. That's going to be 3 by 4, that's 12. And then I also have, so I have 12 from that rectangle there, 3 across, 4 up. And then this is going to be, 1/2 right there. That's going to be 1. So it's going to be adding 1.5, 1.5. It's going to make 13.5, 13.5. And we can keep going. Okay. Now we're trying to find the integral, of 1 over 5x squared minus 20x plus 100. So this looks really scary, but we need to start thinking about this, start breaking it down. Let's see how we can make it easier. All right, let's see how we can make this a lot easier for ourselves. So let's just think about this. Let's look at it, right? Let's think about how we could go across doing this kind of question. All right, so we're trying to find the antiderivative of this 1 over 5x squared minus 20x plus 100. All right, how does that work? How are we going to do that? Let's see. Well, if we think about it, right, we have a couple options, right? So what they're telling us that we have options in arc sine and arc tangent. All right, what do we think about that? What do we think about those options between arc sine and arc tangent? Well, what I think is that if you take the derivative of arc sine, you're going to end up with the square root of something in the denominator, right? So we don't have a square root there, so that doesn't seem like it's going to be arc sine. Right, but we do have an arctan. Right, arctan, the derivative of arctan is going to be 1 over 1 plus x squared. Or no, I might have misspoke earlier and said 1 minus x squared. It's actually going to be 1 over 1 plus x squared. Okay, so how do we deal with that? Let us let's just take the derivative of arctan of x minus 2 over 4, right, like it says right there. Right, and then if we need to do a 1 over 20, we can add that in later, right? Remember to use the choices here, and you don't have to do everything on your own, though it is good practice too. Alright, so we're trying to just take the derivative of that arctangent of x minus 2 over 4. So arctangent of x is going to be, arctangent of x is going to be 1 over 1 plus x squared. So if we're taking the derivative of arctan of x minus 2 over 4, that's going to be, well, what? It's going to be something over 1 plus x minus 2 over 4 squared. Okay, and then in the numerator, we're going to have, well, it should be 1, but we also have to take the chain rule, and we get 1 over 4. So it's going to be 1 over 4 in the numerator. Alright, so let's try to multiply both sides by 16 to get rid of that the stuff in the denominator, right? To get rid of the fractions in the denominator. So multiply by 16 on both sides, and we get 4 in the numerator over 16 plus x minus 2 squared, which is going to equal 4 over x squared minus 4x plus 20. Okay, now that looks decently similar to what we got there. Right, now how do we get that rested in? Well, if we divide by 20, then the 4 is going to cancel out. So we have 1 over something. And then we have to, everything in the denominator we have to multiply by 5. And we get 5x squared minus 20x plus 100. So we are going to use that 1 over 20. And that's our answer. Let's keep going. Evaluate the definite integral. See, the definite integral of a constant is very nice, right? Because if you do the inverse of that, you just get 4x. You plug in 5 and negative 3, well, that's going to be 20 minus negative 12, which is 32. On a related note, notice that 32 is just 4 times 8, and 8 is the distance between negative 3 and 5. If you have a constant, you can just take the difference between these limits and multiply by the constant, and you're done. Alright. Okay, what do we got here? Well, we got the sum from n equals 1 to 4 of 8k minus 6m. That's going to be 8k minus 6 plus 8k minus 12 plus 8k minus 18 plus 8k minus 24, which is this one right here. Right? So that's kind of it. Right? You can't really do anything else with that because you don't really have anywhere to substitute k in. So that's our answer. And we can move on. Graph of f. Let g of x equals 0 to x of f of t. What is an appropriate calculus-based justification for the fact that g has a relative minimum at c? Let's think. Let's think about this. Well, what do we know? Well, well, first of all, we know that f of t is actually the derivative of g of x. All right, think about it. If we take the derivative of both sides, we get that g prime of x equals f of x. So f of x is the derivative. So at x equals c, f of x is 0. F of c is 0. And that's the derivative. So f of c is 0. Right, f of c is 0, and f is the derivative, which means that it's going to have something. It's going to have something, either a relative minimum or maximum or something there. But is that enough? It's not really enough, is it? It could be a maximum or a minimum, right? So we're trying to figure out that it's from below it to above it. That tells us that it was decreasing, now it's increasing. That's a relative minimum. If f is increased, that doesn't really tell us anything. All right, so f plus the x-axis from below it to above it, that is our answer. Let's keep going. All right, now we're trying to evaluate x cubed minus 3x squared plus 5x minus 3 over x minus 1. Kind of complicated, but that is calculus for you. So what I'm going to do is I'm going to use some polynomial long division here. I'm just going to try to divide this out. So I'm going to take x cubed minus 3x squared plus 5x minus 3, and take the derivative, not the derivative, just do basic division, right? Nothing about it, just basic division by x minus 1. So I'm going to do x squared here. I'll show it to you in a minute, hold up. And then I get this cancels, this gets that, and then here, and then that. And then this. And you have. And then you end up with the fact that you have no remainder, and you have x squared minus 2x plus 3 as your quotient. Because this is what I did. Right? You see it's polynomial long division, kind of the same as long division, except you have a bunch of terms and polynomials and stuff. And you realize that you just get x squared minus 2x plus 3. So now you just take the derivative of that, antiderivative of that, and you get, well, you get 1/3 x cubed minus x squared plus 3x plus a c, which is going to be choice A. Choice A. And we can move on to the next question. Alright, integral of this thing. Well, 5x to the 4th, that's the antiderivative of that is x to the 5th. The antiderivative of 3x cubed is going to be 3/4 x to the 4. And then minus 2 is going to be minus 2x. So x to the 5th plus 3/4 to the x to the 4th minus 2x. 2x. And that's our answer. Let's keep going. Evaluate the improper integral if it exists. Okay, so now we're dealing with some improper integrals, right? So we're trying to find the improper integral if it exists. Okay. So how do we find out if the improper integral exists or not? Well, we need to figure out whether it. How do we figure out if an improper integral exists at all? All right. How do we know? Well, we kind of do the same thing that we usually do. The same thing we usually do when we're dealing with an integral, which is that you take the antiderivative of it, and then you just plug in the numbers from 2 and infinity. And if you plug in infinity, and it ends up that like this goes to like, I don't even know, like it goes to like infinity, it diverges, then it diverges, and you have option D, right? Now an improper integral has two ways that it could not exist, which is one, if the denominator becomes 0, right? It's not defined. The problem here would be if we had 0 in there, which we don't. We don't have 0 in that interval at all, so we're good there. Second problem is if we have infinity and it diverges. We're gonna have to check that out to see if that happens. So the integral of 1 over x squared, square root of x, is, well, that's going to be x to the negative 1/2. So we're going to have 2x to the 1/2. All right, that's going to be it. Then you're going to have to put in 2 and infinity, which is going to be 2 times infinity to the half minus 2 times 2 to the 1/2. Well, 2 times infinity to the 1/2. Square root of infinity is still infinity. That's going to diverge. Diverge goes to infinity. Same way we have like a limit that's unbounded, right? This is going to diverge. And so the improper integral diverges. Let's keep going. Okay, so now we are trying to find this thing, whatever this is. Okay. So since we only have one term in the denominator, that's really nice. So we're just going to cancel out each one. So we have the integral of 3x cubed over x cubed, or 3, minus 4x over x cubed, so minus 4 over x squared, minus 2 over x cubed dx, which is going to be, well, 3x for the 3. And then you have, well, it's going to be negative 4x to the negative 2. So you can just write that as 4x to the negative 1. And then you can write it as plus x to the negative 2. So 3x plus 4x to the negative 1 plus x to the negative 2. Take the derivative of that, you get 3 minus 4x to the negative 2 minus 2x to the negative 3. And if you multiply that by x cubed, you get 3x cubed minus 4x minus 2. So this is the same thing, and the antiderivative then is going to be 3x plus 4 over x plus 1 over x squared. Let's keep going. Find values of p and q that make the following equality true. Okay, so this is going to be a partial fraction decomposition. All right, that's another one of our tools in addition to integration by parts, in addition to use substitution. Partial fraction decomposition is kind of cool. Right? As the name suggests, you are just decomposing an integral into fractions, right? Into this thing, you're changing this into two fractions, one of which has denominator x plus 1, the other has denominator x plus 5. And then, of course, you just take you can just do that, right? So how are we going to do that? Well, let's see. So we take the derivative of the right-hand side. You're going to end up with p over x plus 4 plus q over x plus 5. We're supposed to equal x minus 3 over x plus 4 times x plus 5. So I'm going to multiply everything by x plus 4, x plus 5. So x plus 4 is going to cancel out for the p. Then I have p times x plus 5 plus q times x plus 4 is going to equal x minus 3. Okay, so now I just have to find p and q, right? I can take x equals negative 5, right? Because I can take any x I want, right? X equals negative 5. That's going to cancel out this p term, so I have q times negative 1. It's going to equal negative 5 minus 3, or that's going to be negative 8, so q equals 8. Q equals 8. And then I can plug in x equals negative 4. I get p plus 0q, so the q cancels. So p equals negative 7. P equals negative 7. So p is negative 7, q is 8, and that was partial fraction decomposition. Match each indefinite integral to its result where y is greater than 0 and c is a constant. Let's see. So if I don't really want to look at those integrals and like take the derivatives of each one. So what I'm going to do is I'm going to look at the result and take the derivative of that. If I take the derivative of the first one, ln y to the 5th plus y plus c, that's going to give me, in the denominator I'm going to have y 5th plus y, in the numerator I'm going to have 5y to the 4th plus 1, which is going to be like this one right here. If I take the derivative of the one that's at the top right now, then I get the denominator is going to be 5y 4th plus 1, and the numerator is just going to be 20y 3rd. So that's there. And then here, if I take the derivative of that, I get in the denominator, I get 20y cubed plus 5. In the numerator, I get 60y squared. I can cancel out 5 from everything, and I get that integral right there. And we can move on to the next question. Which of the limits is equivalent to the following definite integral? Okay, so this is kind of how we use the infinite limit, the infinite limit to make a Riemann sum. That's what we're doing right here. So we have to start. Right, where are we starting? Right here, it says we're starting at 1 for I equals 1 for each of them. All right, now you have this cosine of pi I over n for 2 of them, and cosine of I over n for others. You're going to start, you have to start from 1 over n, so it's basically just like 0 because n is infinity. And then you're going to end up at, pi, so that's going to be pi n over n, so you have to do pi I. It has to be one of these that you're doing pi I with. Okay, because you're starting with 0, you're ending at pi. Okay, now that's going to be our Riemann sum, and now we have to multiply by I over n or pi over n. Well, each subdivision has length pi over n, since there's pi and you're dividing by the n, right? So pi over n. So that's our answer, and we can keep going. Function g is continuous and increasing. We're interested in the area under the curve between x equals 0 and x equals 12, and we're considering using left and right Riemann sums to approximate it. Order the areas from least on top to greatest on the bottom. Okay. It's continuous and increasing, so it's increasing. So we have the left Riemann sum. Well, that's going to be for this, right? You can see that left Riemann sum goes too low. If you use the right Riemann sum, you notice that it goes too high, right? More than the curve. So you have least is going to be left Riemann sum, greatest is going to be right Riemann sum, and actual area is going to be in the middle. And we can keep going. Approximate the area between the x-axis and g of x from x equals 10 to x equals 16 using a left Riemann sum with 3 unequal subdivisions. Okay, so 3 unequal subdivisions, we're using a left Riemann sum. So we're going to take, well, first one's going to be 2, the difference is 2 times the 5. The next difference is 3 times the 1 on the left, plus another 1 times the 7. That's going to be 10 plus 3 plus 7, or 20. And we can keep going. Alright, we're going to take the derivative of g of x. We're just going to plug the x in. Okay, so we end up with 2x plus 7. Alright, and you take the derivative of x, which is 1, so you just leave it like that. Plug in 9, you get 18 plus 7, 25, square root of that is 5. Right? Not much to it. A freight train leaves the station on an 8-hour trip. The graph below shows the train's velocity as a function of time. How far does the train travel? Right, so this is a PVA question. That means position, velocity, and acceleration. Right? Taking physics, you know, but position is the antiderivative of velocity. Velocity is the derivative of position, and acceleration is going to be the derivative of velocity. So you kind of have that progression. Anyway, we're given a velocity. We're trying to find how far does it travel, the distance. It's going to be the area under the curve. The area under the curve, you have a triangle here, you have a triangle here. That's going to be length 1, up to 50. 1 and 50, it's going to be 25 here, 25 there, or 50 there total. Plus you have a rectangle length 6, up to 50, that's going to be 300. It's going to be 350. 350 miles. And we can keep going. Alright, antiderivative of x to the 5th. Well, inverse power rule, we know it's going to be x to the 6th times something, so 1/6 x to the 6th, because it's going to cancel out that 6 when you bring it down. Alright? See, once you get in the hang of doing this inverse power rule, it goes really, really quickly. Okay. So we are trying to find let's see, we're trying to find the definite integral from 1 to 2 of g of x d of x. Well, we know that the antiderivative of g of x is going to be the antiderivative of g prime of x, which is g of x. So that's just going to be g of x from 1 to 2. So g of 2 minus g of 1. G of 2 is going to be 8 times 2, 16, minus 4, 12. G of 1 is going to be 2 minus 4, so negative 2. So that's just going to give you an answer of 14. And we can keep going. Alright, we are asked to integrate. Alright, for e to the x. What's the antiderivative of that? Well, e to the x is going to become e to the x, which is going to become e to the x. And it's going to become the same thing forever. So we'll just stick with 4 e to the x. Okay? And then we have either this one right here, or you have this one right here. And we need to pick out which one. Well, if you take the derivative of the bottom one, this 5 cancels out, and you just have this, so that's not going to work. Take the derivative of this b, you have minus 5 ln x. The derivative of ln x is going to be 1 over x. That's going to be minus 5 over x. That's answer choice B. And we can keep going. Okay. The following graph shows a Riemann sum. f of x equals x cubed. Which of the following approximates the area between f of x and the x-axis on the interval 0, 2 using a left Riemann sum with 6 equal subdivisions? So left Riemann sum. Right, so we're going to start, how are we going to do this? So we're going from 0 to 2, so each subdivision is going to be length 1/3. Okay, so we're going to be multiplying by 1/3, right, as you can see here. And you have, well, you're starting at 0, you're going to 5, huh? And you're going up to 5, this one right here. 0 to 5 of 1/3 I cubed. Well, that seems to work out, doesn't it? Right, because you're plugging in that 5 in here. 1/3, 5, so 5 over 3, right, because that's going to be 5/3, 4/3, 3/3, or 1, 2/3, 1/3, 0/3. So that's going to be that to the third times a 1/3. So that's our answer. And we can move on. Valeria was asked to find this integral using U substitution. Oh, dang. Wow, that's a lot. Right, and it seems like really complicated. Like how are you ever going to do anything like this? But then you start thinking about this and you realize that they set it up really nicely for you. If you put in U equals x to the fourth minus 3x cubed plus 8x squared, right? Then the derivative of that is going to be that 4x cubed minus 9x squared plus 16x. Right, so do you realize what that means? That means that this entire thing right here and this dx get combined in just du. Just a du. That's it. Right, that was really simple, right? It's just a du. And then this is going to be square root of u. So this is the power of u substitution. We just transformed this massive equation right here into the integral of the square root of u, d. That's it. That's literally it. That's what we did. That is how simple it is. That is why we use u substitution, and that is what we have to choose as u. And we can keep going. Integrate negative 13 cosine of x. Well, the antiderivative of cosine of x is sine of x, so it's going to be negative 13 times sine of x times sine of x. And that's going to give you negative 13 cosine of x when you take the derivative. Remember that if you take the derivative of sine of x, you get cosine of x. But if you take the derivative of cosine of x, you get negative sine of x. Alright, let's keep going. Evaluate the definite integral. Well, 7e to the x, the antiderivative of e to the x is just going to be e to the x, so you're going to end up with 7e to the x from negative 14 to 7. So you're going to have 7e to the 7 minus 7e to the negative 14, which is answer choice B right there. And that's our answer. Alright, so that was this whole unit test on integration. We covered lots of things. We covered integration. We covered integration by parts, U substitution, improper integrals. We covered the whole thing. Right? I understand if you're not in calculus BC, then there are a couple topics that you can kind of ignore. That's being integration by parts. You don't need to learn that yet. Partial fraction decomposition and improper integrals. Right? Those three things you don't have to learn yet because those are solely BC topics. Everything else is shared between both BC and AB. Alright, but that was it for this unit test on integration. I hope you learned something, or I hope you found this video enjoyable, and I hope this helps you in integration and your calculus course in general. I'll see you next time.